Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning together? There is one field called phi, spelled Phi. Phi is the holophase, a cyclic rhythm defined at every point in the universe. Its first derivatives give three simultaneous echoes: time, which we call omega, spelled Omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher derivatives form a branching tree that, in principle, goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, we zoom into just one branch of that tree. In part 11, we sat with phi itself as the silent root. We discovered that if you shift phi everywhere by the same amount, nothing observable changes. Only differences in phi matter. In part 12, we climbed the temporal branch and met omega as the local ticking rate of reality, the way phi turns in time at each point. In part 13, we walked along the spatial branch and met k as the weave of space, the way phi changes from place to place. Now, in part 14 of episode 6, we take a deeper step. We bring time and space together into a single letter of the language, a single object that tells us how phi responds when we move through both at once. This unified letter is called d phi, spoken as d phi. Our goal in this part is simple to say and profound to feel. We want you to experience that change in time and change in space are not two separate stories, but two directions inside one larger kind of change. D phi is the way we write that larger change. It is the first truly spacetime object in the holophase alphabet. Because you are listening with your ears, not looking at symbols on a page, I will describe d phi in words, slowly and carefully. Formally, in the scientific papers, we write something like this. D phi equals omega multiplied by a tiny step in time minus k multiplied by a tiny step in space. For audio, listen to the structure. There are two pieces. The first piece is omega times a small time step. The second piece is minus k times a small space step. Put together, d phi tells you how much phi changes when you nudge the universe a little forward in time and a little sideways in space. Let us make that concrete. Imagine you're standing in a landscape with a strange kind of magical paint sprayed through the air, invisible but real. At every point in this landscape, the paint has a hidden color on a circular dial. That hidden color is phi. As time passes, that color at each point slowly spins around the dial. That spinning rate is omega. As you walk from place to place, the color changes from one location to another. That spatial pattern is governed by k. Now, d phi is the answer to a very specific question. If I move a tiny bit forward in time, and at the same time move a tiny bit in some direction in space, what is the combined change in that hidden color phi? If you only move in time and do not move in space, d phi reduces to omega times your little time step. If you only move in space and do not let time pass, d phi reduces to the contribution from k. But most real motions in life and in physics involve both. D phi is the way we write that combined effect. Here is a down-to-earth analogy. Think about the weather. Suppose you have a weather map that shows temperature across a country at one instant. You can ask two different kinds of questions. At a fixed city, you can ask, how is the temperature at this city changing as the hours pass? That is like omega for temperature, a time derivative. Or you can freeze time and walk from one city to another and ask, how quickly does temperature change as I move north or south or east or west? That is like K for temperature, a spatial derivative. Now imagine you are a pilot flying a small plane. You are not just standing still watching the clock, and you are not only teleporting in space at a frozen instant. You are moving through space while time passes. You can ask, along my flight path, how does the temperature change per kilometer that I travel? That change depends on both how temperature is changing in time and how it is arranged in space. The combination of those two effects along your actual trajectory is exactly the sort of thing that d phi measures for the phase field. So you can think of d phi as the rate of change of phi along a path you actually move along in spacetime. Let us build this intuition more gently. Take our earlier picture of the universe, filled with tiny clock hands representing phi. At every point, the hand points somewhere around the circle. Omega tells you how fast each hand spins as time passes. K tells you how those hand directions vary from place to place. Now imagine that you pick a particular path through spacetime. Maybe it is the path of your own body as you live your day, or the path of a photon of light, or the path of a dust grain floating through air. At each point along that path, you can ask, what is the phase here, right now? That is phi along the path. As you move slightly forward along the path, phi changes. Part of that change comes from the passage of time causing the hand to turn. Part of it comes from the fact that you have stepped into a neighboring region whose phi may be different. D phi is the formula that adds those two contributions together in the right proportions. For an audio picture, imagine walking on a moving walkway at an airport while the lights on the ceiling slowly dim and brighten. If you stand still on the unmoving floor and just watch the lights, you see their brightness change over time. That is the time change. If you freeze the lights at one instant and walk along the hallway, you might find that some regions are brighter than others. That is the space change. Now get on a moving walkway that carries you forward while you are also watching the lights gradually shift in time. The way the brightness changes for you, second by second, is a combination of both effects. It depends on how fast the lights themselves are changing in time and on how quickly brightness changes from one part of the hallway to another, and also on how fast you are being carried. That combined change, for phi instead of brightness, is what d phi captures. Now, why is this unified letter so important in the Holophase language tree? Because up to now we have treated omega and k as if they were separate stories. In part 12, we made you stand still in space and listen to the local ticking rate of time. In part 13, we froze time and asked you to walk across patterns. D phi is what lets us speak about real motions that mix both. It is our first honest way to talk about the behavior of phi in spacetime, not just in time or in space alone. In the scientific backbone of the Holophase framework, which lives in more than 30 papers and is partially archived on Zenodo, d phi plays a central role. It appears in the operators that describe how fields evolve, in the conditions that define special paths, and in the tele expressions that we use instead of the old fluid notion of energy. If you open those papers, you will see d phi written in compact symbols, combined with other derivatives in a careful structure. Here, in the audio series, I want you to understand d phi as a lived idea first, the unified change of phi along your motion. Now, as always, we have to bring in falsifiability. Without that, this would just be a poetic way of speaking. The Holophase framework claims that many of the paths we see in nature are at some deep level organized by the behavior of d phi. In particular, it claims that there are special motions for which d phi behaves in a very simple way, sometimes even staying constant. Photons, massive particles, and other excitations can be thought of as following paths in spacetime chosen by the phase structure. If that is right, then known laws of motion should be expressible in terms of conditions on d phi. Let me say that in plainer language. Traditional physics says that free particles follow straight lines in flat spacetime and curved lines in curved spacetime. Light follows null geodesics. Charged particles feel forces according to electromagnetic fields. All of that is written in the usual language of coordinates, metrics, and fields. The holophase theory says, behind those descriptions there is a phi field. The natural paths of systems through spacetime are those along which the phase change, d phi, behaves in particular constrained ways. Certain motions might keep d phi constant, others might minimize or extremize some tally built from d phi and its cousins. This is not just decoration. If it is true, then whenever we know the path of a system experimentally, we can try to reconstruct what the underlying phase and d phi must have been doing. And whenever we assume a particular phase structure, we can predict what paths should be favored. So here is a falsifiable idea, spoken slowly. Take a situation where we know from standard physics what path light will follow. For example, we know how light bends when it passes near a massive object, from the tests of general relativity. In the holophase version, we can write down a candidate phi field for that region of spacetime, compute omega and k from it, and then compute d phi along different possible light paths. The theory makes a definite claim. The physically realized path is one of the special ones picked out by simple conditions on d phi. If, no matter how we choose phi to match the known behavior of clocks and rulers, we cannot make those special conditions line up with the observed light path, then the holophase framework would fail this test. On the other side, if the holophase description can reproduce all the successful predictions of relativity and quantum theory while using a single coherent structure based on phi and its derivatives, then it earns real credibility. The point is that d phi is not just a nice story. It must do hard numerical work. Let us step away from the equations again and come back to you, the listener, moving through your day. Every experience you have is embedded in both time and space. You are never just a time point or just a place. When you walk across a room, you are a world line in space-time. There is a phase value associated with each event along that world line, and a d phi that describes how that phase is changing as you move. You do not feel phi directly, but you feel the consequences. Light patterns, sounds, touches, and internal states that are organized by underlying phase patterns. We can use a very simple personal analogy. Imagine a song again, but now imagine that instead of just listening, you are dancing through a room whose lights are synchronized with the music. The volume of the song is like the time-based change. The position of the lights in the room is like the spatial structure. As you move, what you experience is not just the volume and not just the arrangement, but the combination. Flashes of light and beats of sound along your own path. d phi is like the mathematical description of that combined experience, but for the fundamental phase field. Another analogy is a river with a temperature gradient. The river flows through a landscape. At every point along the river, the water has a temperature that changes in time with the weather and also changes along the length of the river as cold springs or warm inflows join. If you drop a little sensor into the current and let it drift, the sequence of temperatures it records depends on both the time evolution of temperature at fixed points and the spatial variation of temperature along the river. The derivative of temperature along the actual path of the sensor is the analog of d phi for that situation. You might ask, why is d phi a letter in the holophase alphabet rather than just a convenient shorthand? The reason is that the language of reality in this model is about how phi and its derivatives structure motion, form, and tally. Omega and k are important, but many of the real grammar rules involve both at once. DeFi is the simplest way of packaging change with respect to time and change with respect to space into one symbol. From DeFi, higher objects are built. Curvatures in spacetime, propagation operators for waves, tally expressions that count how much structure change is happening. Without DeFi, those constructions would be fragmented. You can think of it like moving from separate letters to a digraph in human language. In English, we have the letters T and H. Separately, they have their own sounds. But the combination TH appears so often and with such a special role that we practically treat TH as a unit. In the Holophase language, omega and k are like T and H, and dphi is like TH, a fundamental combination that deserves its own place in the alphabet. Now I want to address a subtle point about clarity. In the old way of speaking about physics, people often talk about fields in space-time. Space and time are the stage, fields are the actors. In the holophase view, the phase field and its derivatives are more primary. Space-time itself, with its structure of near and far, fast and slow, straight and curved, is read off from patterns in phi and from how dphi and its higher relatives behave. This is a strong claim, and again, it is only acceptable if it survives contact with data. A good listener question here would be, if dphi is so central, why have we not been talking about it all along? Why did we separate omega and k in the first place? The honest answer is because your intuition needs to see the pieces clearly before it can understand their unification. If I had started episode 6 by saying, there is a single differential object dphi that unifies time and space, it would have sounded impressive, but empty. By taking time to walk you through omega and k separately, to let you feel time as a local cadence and space as a pattern of variation, we have now earned the right to put them together. You can feel what is being glued. Let us also be honest about the limits of intuition. Even with good analogies, dphi remains a subtle idea. You cannot see it with your eyes. You cannot hold it in your hand. But you can train your intuition to sense what kinds of questions it answers. Anytime you find yourself wondering, if I move through this situation along this path, how does the underlying pattern change for me? You are asking a dphi type question. Before we close, let me take you briefly behind the curtain of the formalism again, but in plain words. In the Zenodo papers, dphi appears in constructions that look like total derivatives and covariant derivatives. These are technical ways of saying we are measuring change along paths that are themselves living inside a structured arena. The holophase model uses phi and its derivatives to build that structure from the ground up. dphi is the simplest of these path-based change objects. From it, we can define what it means for a path to be phase straight, or to trace a line of constant phase, or to minimize a tally built from squared derivatives. All of these ideas have concrete experimental consequences. They tell us where we expect light to go, how waves will bend, how interference patterns will form. If experiments show that we can always choose a phi field and a dphi structure that reproduces the observed paths and patterns, then the holophase language survives another test. If we eventually find a robust phenomenon that absolutely refuses to be described this way, no matter how we adjust phi within the rules of the theory, then the holophase language, at least in its current form, would be incomplete or wrong. This is the risk we accept when we turn a beautiful language into a scientific proposal. Now, as an audio listener, you might wonder how to carry the idea of dphi with you in everyday life, without equations. Here is a simple practice. Pick a familiar walk in your day, from your bed to the kitchen, from your door to the bus stop, from the bus stop to your work. The next time you walk it, bring a gentle awareness to two things at once. First, the passage of time, the sequence of moments, the rhythm of your steps, the beating of your heart. Second, the changing scene around you. Walls turning to open street, trees appearing and disappearing, sounds shifting. Feel that your lived experience is always a blend of time passing and space changing. Then, in your mind, give that blend a name, d phi. You're not calculating anything. You're just remembering that there is, in principle, a single underlying pattern whose change along your path could be described. This is not yet physics. It is training your intuition to think in terms of unified change rather than separate categories. Later, when we speak about motion v being the special velocity that can make d phi behave in certain ways, this intuition will help. You will already be used to the idea that by choosing how you move, you can shape the way the underlying pattern shows up for you. Before we finish, I want to spend some time on one more important viewpoint that will help you later when we talk about tallies and counts in the holophase model. In ordinary physics classes, people are taught to think of energy as a kind of invisible substance that can move around and transform, but not be created or destroyed. It is easy to imagine energy as a fluid filling things. In the holophase framework, we do not treat energy as a mystical fluid. Instead, we treat it as a disciplined way of counting structure change in phi and its derivatives. Tallies built from d phi and related quantities tell us how much organized variation is present along a path or inside a region. Why am I mentioning this in a part about d phi? Because d phi is one of the raw ingredients that these tallies are built from. If you want to count how busy a region of the phase field is, you need to know how strongly phi is changing as you move through spacetime. D phi is the basic building block that answers exactly that question. When you later hear in the written papers about tallies that look like integrals of certain combinations of derivatives, you can remember that underneath the symbols there is a very simple intuition. We are counting how much d phi and its higher relatives are active along some path or surface. This leads to another falsifiable idea. If the holophase tallies, built from d phi, really do correspond to what we traditionally call energy and related quantities, then whenever we compute such a tally for a system, it should line up with actual measured numbers from experiments. For example, if we have a vibrating string, we can describe its phase pattern, compute the appropriate tally constructed from d phi and spatial derivatives, and compare the result with the measured spectrum of the string. If they disagree in a way that cannot be fixed by improving our approximations, then our chosen tally, or even our whole way of treating energy as a count of structure change, would have to be revised. On the other hand, if again and again the tallies match observations across very different systems, that is strong support. Light beams, sound waves, oscillating circuits, quantum systems, all can be tested. The point is not to worship the word energy, but to insist that the numbers we compute from d phi must meet the numbers we measure in the lab. That is the contract with reality. I also want to turn briefly to how d phi fits into the bigger master tree picture in your imagination. When you close your eyes and visualize the master tree of the holophase language, you see phi as the glowing root, omega and k as first branches, and then a rich forest of higher derivatives above. D phi is like a subtle, slanting branch that connects the time tower and the space tower. It does not sit purely on one side. It leans across, reminding you that time and space are not independent alphabets, but two directions inside one larger sheet of change. If you like geometric images, you can picture a flat sheet representing space-time, with one axis for time and one for a chosen direction in space. At each point on this sheet, there is a little arrow representing the gradient of phi in that combined sense. D phi is what you get when you project that arrow along the direction of a path drawn on the sheet. The steeper the arrow points along your path, the larger d phi is. The shallower it is, the smaller d phi is. A path with zero d phi is like walking along a contour line on a mountain map. The height does not change even though you're moving. In holophase language, such paths trace lines of constant phase. You can even turn this into a small mental exercise. Next time you look at a topographical map, or even just imagine one, pick a contour line, one of those curved lines that show equal height. If you walk exactly along that contour, the altitude does not change. You are moving through space, but the height tally stays constant. Now imagine turning that picture sideways into spacetime. Instead of height, think of phase. Instead of contour lines, think of world lines of constant phase. d phi equals 0 along those paths. All real waves are built from structures that care deeply about such phase relationships. Finally, there is a gentle emotional point that I want to acknowledge. It can be dizzying as a listener to hear words like spacetime, derivative, and phase over and over. You may feel at times that you are barely holding on, that these ideas are always slightly out of reach. I want you to know that this is normal. When you learn a new human language, there is a phase where you can recognize sounds and shapes, but cannot yet speak fluently. The holophase language is no different. Each part of this episode is like an immersion session. Even if you do not remember every term, your nervous system is slowly building an intuition for how this code works. So if you are feeling a little lost, it is okay. You are still participating in the experiment. The experiment is that a deep, mathematically precise model of reality can be told to you as a story, in simple spoken words, without hiding its commitment to falsifiability. Your role as a listener is not to nod along politely, but to keep a part of your mind sharp and skeptical, asking, how would we know if this is wrong? Whenever that question arises, you are aligned with the spirit of the scientific papers behind this series and with the spirit of the Holophase program itself. Salam and peace be upon you as we close part 14 of episode 6. We have taken our first real step into space-time thinking within the holophase language. We have learned to name d phi, the unified letter that tells us how the phase field changes when we move through time and space together. We have seen how it is built from omega and k, how it appears in the formal backbone of the theory, and how it can, in principle, be tested against experiments. And we have hinted at the next move in our journey, using d phi to define special paths and motions. In the next part, part 15, we will follow that hint. We will meet v, the motion echo of phi, as the velocity that rides the pattern, the speed and direction that keep the phase constant along a moving feature. There we will see how d phi becomes the key that locks time, space, and motion into one triunity, not just as philosophy, but as a sharp, testable structure. For now, carry with you a simple memory. Behind your day of walking and waiting, of sitting and standing, there is a single underlying phase field. Omega tells you how it turns in time, K tells you how it twists in space, and d phi tells you how it changes along the actual path you live.